Hello, welcome to the Maps Talk. I'm going to introduce our speaker today, Roger Wiens. He's a planetary scientist and fellow at Los Alamos National Laboratory. He has his bachelor's in physics from Wheaton College and a doctorate in physics from the University of Minnesota. He's the project leader for both the ChemCam instrument aboard the Mars Curiosity rover, currently operating on Mars, and the new SuperCam instrument for the Mars 2020 rover. A couple of things. He was knighted by the government of France for his work in forging strong ties between the French and American scientific communities and for inspiring many young, ambitious Earthlings. He is the author of a book, Red Rover, Inside the Story of Robotic Space Exploration from Genesis to the Mars Rover Curiosity. Other awards, he has an honorary doctorate from the University of Toulouse, and he is not the first scientist that we have on our maps talk that has an asteroid named after him. So he's the second. So he has asteroid 41795 Wiens. I'd like everybody to welcome our speaker, Roger Wiens.
Thank you. It's great to be with you tonight. And yeah, that's my instrument, SuperCam. Unfortunately, I don't know how to get it to spell forwards instead of backwards on that poster. Let's see, I'm going to go ahead and share my screen. And so let's make sure this all works. And this should be the title slide coming up right there. So somebody let me know if it is not showing, otherwise I'm just going to charge ahead. So it's great to be with you tonight. I've been able to be around the world virtually and in many different kinds of events, and so we have to count it a privilege as well as the other aspects. So happy to be with you tonight. I wish I could actually be there in person because I love traveling, but we're happy for this kind of thing for now. So we have this great thing going on. I mean, there are 2 one-ton rovers actually working on the surface of Mars now. And we are really trying to understand this planet because there are 2 planets in our solar system that are within the habitable zone. And that's kind of this Goldilocks zone where it's not too cold, not too hot, but just about right. And in fact, if Mars had been a bigger planet, more like Earth, it would be very habitable. Even though it's a little farther from the sun. But in fact, Mars is only 1/10 of the mass of the Earth. And because of that, it has less gravity and about 38% of Earth's gravity. And that's enough less that it has lost its atmosphere over time. It only has 1% thick as atmosphere as Earth's. And with that, it cannot retain its water. So Mars was habitable in the past. It is not very habitable now. And so our mission is really to go back in time with Mars to understand what it was like back then, maybe whether there was life on Mars at that time, just microbial life, and to understand what things were like, if we can find life and so on. So NASA has had this prolonged program of rovers. And I'm going to take you back to the first one, which was Sojourner in 1997. It was at the dawn of the internet era, and it was a big hit. It was I think it just about took down the internet at that time. It was followed in 2004 by twin rovers, Spirit and Opportunity. While Sojourner lasted less than 3 months, Spirit lasted about 5 years, and Opportunity lasted all the way until 2018, 3 years ago. And then a dust storm did it in. These had solar power, and they're fairly small. So the scientific community longed for the day when we could have a whole sort of mobile laboratory on Mars to look for organic materials, precursors of life possibly, and all of that. And so in 2012, we got our wish with this rover called Curiosity. And that's the one that is still operating on Mars today, along with Perseverance, which I'll talk about a little bit later. But first of all, with an introduction to Curiosity, which still has my instrument on it, ChemCam, Curiosity went to a crater that's near the equator on Mars called Gale, landed there in 2012. This is the lowest spot for within 700 miles. It's a very low point on Mars. And if we're going to look for water on Mars, this would be the place. because there's gullies coming in from the south that you can hopefully see there if you can see my mouse. And then there's this nice kind of mountain in the middle. It's 3 miles high, and it looks like it was made with dry material. And so the whole mission was to look for water, evidence of water, and then start to climb Mount Sharp and look for evidence of drying out of Mars's climate. And so that's what this rover's been doing for the last 8 years. This picture was taken by Curiosity once it's climbed up nearly 1,000 feet up onto Vera Rubin Ridge. And so looking back on the places where it had been at the landing and shortly thereafter in the years 2012 to 2014. Then it crossed this dune field called Bagnold and started climbing the lower part of Mount Sharp. And so looking at this reconstruction of the topography, this shows the track that the rover has gone on. And some of the highlights: we were on the ridge in 2018, climbed up onto this pediment in 2020, and we're way over at the edge now of the what we call a sulfate unit. So we're just about to start studying that, just getting out of the lake bed sediments. But we've climbed over 1,000 feet in lake bed sediments, showing that this lake, which is 90 miles in diameter, the crater is 90 miles in diameter, and this lake must have lasted a very long time to lay down all of those sediments. And then we're going to go up into this valley up here. So the terrain just keeps on getting cooler and cooler. So even though Perseverance is the latest rover, I think Curiosity still has, hands down, has the winners for being in the best topography. It's really cool. So keep on watching this rover as you can. This is a selfie that it just took 3 weeks ago. And the rover has now climbed up on top of this about a 7-meter high cliff. It went around the back, didn't climb up the front, and it's now working to drill a hole up there on the top for sampling. So the major discoveries with Curiosity are listed here, along with this artist's conception of the lake that would have existed 3.5 billion years ago. So we found when there were many people that were doubting that water had lasted on the surface of water of Mars as open lakes, we really discovered and proved that there was long-lasting liquid water, and there might have been a series of lakes, but at least about 1 million years where this was a lake. And this was not salty. It was a near neutral fluid condition, so kind of like the Great Lakes in the central U.S. perhaps, or Lake Tahoe, only a lot bigger. It was fresh water. As our scientist said, our lead scientist said at that time, you could have put it in a glass and drank it. And then we have also found that the building blocks of life were present. So there's this acronym here, CHNOPS. That stands for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And then we added boron as well. We found all of these elements are present, and these are the building blocks of life. And also Curiosity found organic carbon. We found long chain molecules. We didn't find amino acids or fatty acids yet, but we found a lot of the things that are that might be degraded from those. And remember, this surface has been pummeled by radiation for millions of years. So that's pretty exciting, and it's a lot to have discovered for this mission, and there's still more discoveries to come. So stay tuned for that. Now, we talk about that being 3.5 billion years ago. It turns out that Mars' surface is mostly ancient. If we take a sort of a poll, if you will, of the age of rocks or the surface on the Earth, it's probably averaging between 100 and 400 million years, which seems like a long time, but it doesn't hold a candle to Mars, because most of Mars' surface is more than 2.5 billion years old. That's because Mars just didn't have a lot of things weathering its surface, and it doesn't have active plate tectonics. And so because of that, Mars is this ancient surface, and we can go there almost like going back in a time machine in our solar system to look at what was happening back then in our solar system. And the things that were happening when most of that surface was being created on Mars is that we had the earliest fossils on Earth, things called stromatolites, and then even the earliest evidence of water on the Earth. And in fact, if we look at that in a little more detail here in this slide, you know, the fossils that we think of were all all occurred during this green thing here called the Phanerozoic, means the appearance of life. But there was life long before that in the Earth, but it was single-celled or single-celled colonies, like microbial mats or slime. And that has gone on up to about 3.7 billion years. This LUCA is the last universal common ancestor for all of life. And so back to that time when we have the earliest evidence of life on Earth. So that's kind of the time frame that we're looking at when we go to study the surface of Mars. And so looking at this slide, talking about what should we look for, we're not looking for macro fossils like ancient fish or ancient leaves. We're looking for these rock layers that you see on the right-hand side with the finger pointing to these cones or domes. And what happened was that was the first time that you had sticky or slimy material that caused the sediments to stick in a non-flat configuration. And so we started seeing these things in the sediments. And we find carbon in these. And in fact, the best preserved of these are in a few different places in the world, but the best ones are actually in the outback in Australia. And so I actually took a trip there in 2019, and this is the Trendle locality, if any of you know about it. And right behind me on on the left, as you look at this picture, that rock there that is outcropping above the cliff is just filled with stromatolites, these domed formations. And so got to study them. And the idea was, if we're going to find something like that on Mars, we need to know what it looks like on Earth. So a bunch of us from the Mars teams went out there. So here are the two rovers that are active on Mars now. And so we have Curiosity on the left, and it has 10 instruments. It weighs about a ton. Perseverance on the right beats it by a little bit, about almost 300 pounds. And it's almost the same. Basically, NASA said they saved money by using 650 drawings of the parts from Curiosity to build Perseverance. But it's got fundamentally different in mission in many ways. And it's got 7 instruments. It's got this helicopter as well. And then it has a sample cache where it's going to be collecting samples that are going to be prepared to be returned to Earth by this rover. So we're going to talk about all of that in due time here. So first of all, just going back to the goals of these missions, Curiosity was to study the biological potential, look at the geology, the habitability, and look for or study human hazards. Perseverance had some of those similar goals for exploring geology, looking for habitability, seeking signs of ancient life. But then it has these two at the bottom to gather samples that could be returned to Earth by a future mission, and then demonstrate technology for a future robotic and human exploration. And so we'll talk about all of these as we go along here. This is a nice picture showing the rover, and it kind of highlights the different instruments. We have 7 instruments on this, and they're all new. In fact, I'm the only person who has led an instrument on Curiosity and is leading another instrument on Perseverance. So we'll highlight these in turn. First of all, the remote sensing. We have stereo cameras called Mastcam Z, and we have my favorite instrument, SuperCam, that I lead, and they're up there doing the remote sensing from the rover. Then on the right, we have the proximity instruments, which are Sherlock and Pixel, and these are do fine scale mapping from the rover's arm. And so Pixel, I'll just highlight right here, it does mapping of the elemental compositions from this kind of white box you see on the upper left on the arm. And so it uses an X-ray technique to do that. And so it wants to look at the kind of the shape of minerals by the configuration of these elements and all of that. And so we're still looking forward to its use. It has not gotten pulled out yet on the surface of Mars. Then we have an instrument called Sherlock, which has the best acronym of all of the instruments, but it uses a laser, a small laser on the end of the arm, and in the ultraviolet to look for fluorescence and a type of mineral spectroscopy called Raman, and to look for organic materials, and it's quite sensitive to them in the parts per million. So we're looking forward to that one as well. It has not gotten pulled out yet on the rover. And so this kind of just shows us, going back to stromatolites on the Earth, what these can do. And so they can map the make element maps with pixel on the bottom, and then on the top, it can actually make maps of organic material in these materials. So that's really the goals of these two instruments on the rover's arm. And you can see how it's illustrated with ancient life on Earth. So now going to the environmental measurements, META is a Spanish weather station, and it has a number of different components. It looks at the humidity, the wind, speed and direction, the pressure, all of those things. While RIMFAX is a radar system that looks underground. And so this is provided by the Norwegian Defense Ministry, and it is looking for layers of rocks underground. And we've seen the first of those, and they look pretty cool. So they can tell us whether there's solid or rocks or soil going way down. And so we're just getting the very first maps of that as the rover is driven just a little ways. And then we have these cool things. I'm going to defer till later with the helicopter, but MOXIE is an instrument that is creating oxygen on the surface. Now, the thin atmosphere of Mars is almost only CO2, almost no oxygen there as O2. So we couldn't breathe even if the air was thicker, but plants could grow, and that's kind of a cool thing. But for astronauts, or even to produce oxidizer for refueling, we have this tech demo, and it's producing about 10 grams of oxygen per hour on a catalytic bed from CO2. Now, that's only about a quarter of the needs of one human, so this would clearly have to get scaled up for a future mission. But we're showing we can do it on Mars. So that is just getting started, perhaps even within the next week on the rover. And so now, just going to where this rover is now, we picked a spot that is right on the edge of Isidis Impact Basin near Syrtis Major, which is if you ever look through a telescope, it's a dark area on Mars. I used to, when I was a kid, I sketched the features of Mars, and Syrtis Major was one of our favorite features. And so we're going to this little crater, which looks very little here in this picture, called Jezero, that's right on the edge of these things. And we're going there because of some really cool things. Jezero crater is about 25 miles in diameter, and it has a river, in fact, 2 inlet valleys and 1 outlet valley. And at the inlet of these rivers, we see this really cool formation you see on the right, which is a delta formation. This is the same kind of thing that the Mississippi River or your favorite river that empties into an ocean is producing in that body of water. And so it is laying down all these fine-grained sediments and then producing these meanders that you can even see in there as the river channel changes over time. And we have mapped this river delta from orbit with orbital instruments, and that's shown as this overlay, and showing that there are different materials in here. There are clay minerals in the delta itself, so that's pretty cool. It's not unexpected. There's olivine, which is more of a volcanic or igneous mineral that's down on the floor of the crater, and then there is around almost like a bathtub ring around the crater, there is magnesium carbonate. We have a lot of carbonate minerals on Earth. It makes limestone. It's everywhere as a sedimentary rock. But Mars, even though it has a CO2 atmosphere, it does not have much carbonates, and we're trying to figure out why. So that's one of the things we'll figure out here. Now, if you can see my cursor, I'm going to point to where the rover landed. If you take these 2 craters right here that are just down from the delta, we landed like a triangle right below them, right there. And you'll see that in just a little bit. So that's where the rover is now, in a little bit in the olivine area that it's showing there. So river deltas are habitable environments, and they bring down a lot of nutrients, a lot of on Earth. They bring down a lot of organic material. And in fact, if you think about where we go for, say, coal deposits on Earth to mine coal, it is in ancient river deltas that have been covered over, and they're from many ancient eras on the Earth. And so there's a lot of organic material on Earth that gets brought down into a delta. So that's why we're going to this delta here on Mars, and because they're so good at concentrating and preserving organics there. So on July 30, I was expecting to be at the launch pad to see our instrument and our rover off. But of course, this last year took a different turn. And one of the biggest disappointments of my life, I could say, certainly of last year, was not being there for this launch. But of course, the more important thing is that we all survived, and so that's a good thing. And we could still do this mission. If you ask me later, there were some moments where we didn't think this would get off with the COVID pandemic happening, but fortunately, it all did work. And so then the landing occurred on February 18, and I hope many of you actually watched it maybe in person live then. I've got a video. There is sound with this, so I hope that this all works for your screen. You may need to turn up the sound a little bit. So here it goes. So it takes about 8 months to get to Mars. And this capsule is going to slow it down from about 16,000 miles an hour. It's going streaking across the sky there in this animation. We've got a combination of animation and real pictures coming up here. This is a real picture of a parachute deploying. So there it goes.
Navigation has confirmed that the parachute has deployed.
Animation here of it. And so we're going to get some real pictures again as this thing gets to the ground. And here it comes. You can see the rover going down on the left, and it's hanging from the sky crane. And that's how it happens. And I can tell you, I was watching this video from home, but I was really on pins and needles. I was not sure this was really going to work the way it was supposed to. But there's some really cool things here. This is a picture that was snapped from an orbiting satellite going around Mars. And I think it's from 380 kilometers up. And it got this great picture of the river delta that you can see, delta formation that you can see here. And then if you look up really close in this image, you can see the parachute and the capsule coming down in this image. And so that inset helps us there. Just to remind you again of exactly where the landing was, it was right in here. And that descent stage actually had radar and images of the ground to tell it where to direct it for a nice soft spot, because there's some pretty rough areas here. In fact, just to the left of where the rover landed, this area right here is called Sita, and that's a very rough area. And so it diverted and just landed in this smooth area right here. And you'll see that it's really quite smooth in the images that come up. And these are the iconic images that we have from that landing. There were cameras both on the rover looking up, as you see on the right, seeing the descent stage sitting there above the surface, hovering, lowering the rover that you see on the left from the cameras on the descent stage and until it touched the ground. And then as soon as it was firmly on the ground, all of those 4 cables were cut and the descent stage flew away. Its job was done. And this is the first time that we've ever seen a picture of the landing on another planet. So that's really cool. Now, the Curiosity rover had the same technique, but it didn't have the cameras to show it, except for one camera that was looking down from underneath the rover. We didn't get these pictures back in real time. They were beamed the next couple of days after the landing, but we were just, our jaws just dropped when we saw these pictures. They're so amazing. So hats off to JPL for such a great landing. This was the first picture that we actually got. So just a couple of minutes after the landing, this was beamed up as a thumbnail, and we got to see that the wheels were on the ground. So the rover landed right side up, you could say, and we started to see the terrain around us. And that was pretty cool. So here's a close-up now of where the rover landed. And so you see Perseverance right there in the center below those two craters, south of those two craters. And then you see the other parts of the landing descent with the parachute, the descent stage, and the heat shield, all in slightly different places. And they're about a little less than a half a mile away in most of these cases. So, and there, here you can see how rough the area is just to the left, just to the west of where this rover is. So the descent stage was programmed, and it's also rough to the right. So it did a really great job of finding this little spot where it's smooth. So now the first scientific instruments that were unpacked is basically on day 2 of the mission. The mast was deployed. It was stowed against the deck of the rover. And then we started to get pictures from Mastcam Z, which is this great stereo imager. And so getting the first picture, some of the first pictures, here's the back of the rover. I like this because our SuperCam instrument has all of these calibration targets sitting right there. Here is the antenna for the helicopter. So that's what communicates with the helicopter. These are more calibration targets for the Mastcam right there. And back over here is the RTG, which powers the rover itself. So starting to get, it basically got a 360-degree panorama. It could pick out a lot of detail way off in the distance. We have these very interesting rocks in this region right here. It seems as if the parts that stick up are dark, whereas the parts of the same rock that are at ground level are lighter colored. And so we're trying to understand some of that. This one was named Harbor Seal because of its crazy configuration. And so the weathering on Mars is quite different from Earth. It's very wind centric. And so we get these rocks that are we call them ventifacted. They get into pyramid shapes sometimes, or in this case, if you have harder parts of the rock, they remain while the softer parts get whittled away. So very interesting. This is what we call a delta remnant. We think this is part of the delta formation that the rest of the delta eroded away from this over the several billion years. But this part was for some reason a little bit harder, and so it's a little closer to the rover. It's about 1.2 miles away, whereas most of it is more like 1.6 miles away. And so this is an image. We may get an image of this with SuperCam in the near future, which gives us a little bit better resolution than the Mastcams. So the second instrument to get worked out, to unpacked, if you will, what is SuperCam. And SuperCam has about 5 different techniques that we use. When we proposed this to NASA back in 2014, we thought we were being way too ambitious, but NASA liked the idea, and so we were stuck with building it. And so we at Los Alamos National Laboratory partner with the French Space Agency, and this is a partnership we forged more than 15 years ago with ChemCam, and it's just gone extremely well. We love working together. We get a little bit of French cuisine and a trip there from time to time. And half of this instrument is paid for by the French government. So the American taxpayer wins as well. So it's a win-win situation. But we have a technique that's shown in the lower left, which uses a very focused laser pulse that ablates a little bit of material off of rock, and it comes off in excited state such that it gives off light. It's actually a ball of plasma. And we look at that, and it gives us the atomic emission spectrum of the material in the rock. So it gives us the chemistry of the rock. So that was the basis for ChemCam. And then SuperCam added green, and made it so the laser beam could change to green color. And we use a mineral technique that uses the green beam. And then we get infrared spectra, and we have the microphone to give us sound, and we have the camera. So those are all of our techniques. Here's that green beam flashing. It is just gigantically brilliant green. And of course, it is an eye hazard on the Earth, but not on Mars because there's nobody there. So our first target, we got to a target called Mars. And in fact, I was just in a meeting with a with a Navajo engineer earlier today. He's Aaron Yazi is a Navajo origin, and he is working as an engineer, a mechanical engineer at JPL. And he and Katie Stack worked out the fact that some of our first targets are being named with Navajo names. The reason for that is that this rover landed in a well, let me back up just a little bit. The scientists mapped the terrain before the rover got there. And just like we have topo maps on Earth, we mapped it by quadrangles. And each quadrangle is named after a national park or national monument around the world. Well, the rover landed in Canyon de Chelly. And if some of you have been in the Arizona desert, you might have been there. It's a national monument in the Navajo Nation. And so since we landed in Canyon de Chelly, we are using Navajo names and approved by the Navajo Nation tribal government. And so this was the very first target, and it was named Mars appropriately, which is the Navajo word for the planet Mars. And so we shot this with the infrared laser for our elemental compositions, and this is what we got. This is what the color spectrum looks like for us. And in fact, those are the colors down below that we would see with our eyes. So this goes further into the ultraviolet and further into the infrared than our eyes can see. But what we see here are a lot of peaks, a lot of that in each one, depending on exactly where it is in the wavelength spectrum, it tells us what elements are present there. And we calibrate these intensities to give us a composition. And we know that Mars is, and in fact, other rocks in the vicinity have a composition that is roughly what we call basaltic. It has minerals that are of the variety of feldspar and olivine and pyroxene, kind of common on Earth, especially in the mid-ocean regions, but also in some places like basaltic flows in Oregon and so on. So we're still trying to understand exactly, is this igneous mineral grains that were cemented together in a lake, or what is this a primary igneous rock? So those are some of the questions we're still working out. We also have this microphone, and the purpose of the microphone is actually to study physical properties of the rock. This microphone is going to tell us, we think, how hard the rocks are without ever touching the rock. And the way it's going to work is that we actually listen to the zapping sound that the plasmas make when we shoot the laser at the rock. And they actually change if the rock is soft. They kind of stay about the same if the rock is hard. But we also can listen to the wind, and there's another microphone as well on the rover, and so we can both listen to the wind. I've got a recording here. I'm not sure if you're going to hear it on your computers or not, but I'm going to play a little bit of it. So maybe you're hearing that. That was the first recording of wind on Mars ever. And now here is the laser zapping sound. And again, it's kind of quiet. Little tick, tick, tick. I don't know if you're hearing it or not. Anyway, and so we're starting to get that out and use it. And here is the imaging capability of SuperCam. Because we're using this through a telescope, we actually get these images that look like they're spyglass in shape. They're round. And so we stitch them together into a mosaic. And so here is part of the Delta Formation, almost 1.5 miles away. And we've got the resolution with this telescope to actually spot a softball at 1 mile away. So this is pretty good resolution. And you can see rocks and layers in this Delta Formation. So we're pretty jazzed about what we can see even from here. And this is another camera. It's mounted in the same box as Sherlock. And so Sherlock's on the left here, but Watson is on the right. And so that's a camera that we got out now for looking at the helicopter, which you're going to see in just a minute here. So this is the Mars helicopter called Ingenuity. And so it is about 4 pounds in weight. And most of that weight is actually the battery, a lot of it. To get this thing going, it has, the blades are 1.2 meters in diameter. That's about 4 feet. So Spread your hands about 4 feet across. That's fairly big blades actually, and they have to go spin up to 2,400 revolutions per minute. The speed of the blade is getting up to the speed of sound near the edge. They have to go so fast because of the thin air. And so this is a tech demo. It's designed for 5 flights. Here it is all folded up on the bottom of the rover. So the rover's flipped over. We're mounting this, and it's all folded up. You can see the actually the thing that is coming right next to us here is one of the legs, landing legs of it. And then there's a solar panel up on the top here. So you'll see what it looks like once we get it out. And then there was a cover that was placed on over this for the landing. So the rover jettisoned the cover first, and then we started to see this happening. And so there it actually got part way off of the bottom of the rover, and then it hung like this. And then we dropped it at the beginning of last week, about 9. I think it was about just a little less than 2 weeks ago. And then the rover had to drive off right away so that the Ingenuity could get solar power to stay alive from its solar panel. Now we've designated an airfield on Mars. This is the first airfield on another planet. And so the rover landing spot is right there. And then there's a flight zone, which is designated. Now the rover right now, Perseverance, is right off just a little bit under the A of airfield. We're about 60 meters, I think about 60 meters away to give it lots of space. And then it's going to fly. Now it was supposed to fly last weekend. And in fact, there's a spin test that was done just a little over a week ago. But then there was a fault condition on the software. And the helicopter team has been studying that for the last several days, since last Saturday. I think they have a solution to the issues. And so at this point in time, we think this helicopter is going to be ready to fly just about any day now. And so really stay tuned to the news, and we think it's actually going to happen this time. So stay tuned. So this is the idea that it would take off from where it's at. It'll take images as it flies. It's going to do a little bit of a loop. It has a potential landing site if it has to land early, but otherwise it's hoping to come back around and land back in the same place that it took off from. And it's going to be doing hopefully several flights if successful. The tech demo is really on the hairy edge of being able to do this. The design has very narrow margins. But I'm excited about this, not just because it's cool to do, because this could enable new science on Mars. There's actually a rotorcraft that is being built for Titan, which is a moon of Saturn, which has a thick atmosphere. But on Mars, if we could get a rotorcraft in this thin atmosphere, there's places we could go that we could never go otherwise. And so this is one of my favorite places that I would like to go with a helicopter on Mars eventually. Not this one, but a future helicopter. This is a cave on Mars. Turns out that Mars has lava tubes. And if you are familiar with any of them in Northern California, they can go for quite a long distance. And usually sometimes the opening is a cave-in, what we call a cave-in, or just a collapse of the ceiling in one place. And that's the main openings that we have on Mars. And these are big ones. This is 150 yards in diameter. And so I've been working on a prototype instrument that could be a lot smaller than SuperCam, hopefully small enough that could go on a helicopter. And it would be really cool to look for organic material in a cave where it would be protected from the environments that we have on the surface. And so this was an R&D 100 entry for a national or international R&D contest this last year. And we actually won on this. So this is our organic cam, which is supposed to be a follow-on from SuperCam that could be very lightweight and study organics in a Mars cave or on another planet. So we're really excited about that. So go helicopter. That's my mantra right now. Anyway, now we have this whole concept of the samples that are going to get collected for Earth return. So Perseverance, all of the rovers that we have on Mars, they're still there. They cannot get off the surface because nobody built rockets for them to get off the surface. But I'm going to tell you about how how we're planning to get materials from Percy back to Earth eventually. So the samples are going to be part of a drill core. So the drill that Percy has is hollow. And so as it drills, it's going to be collecting material inside of that drill tube. And in fact, there's a special titanium tube that it's going to use to encapsulate that material. So I've got a little video here that I think will work, and it'll show you the drilling and then bringing it into the rover. It's all very mechanistic. So here it goes, and now it's bringing it back to the rover with the core inside of a tube. And so it docks with this turret right here. That turret brings it down into the sample cache system on the rover, and there it is transferred to an imaging station, a capping station, and then to a storage area. It doesn't show all these steps in this video, but it does show you the storage area that it puts it in over here. Now, we don't want these tubes to be left in that storage area when the rover dies or when the rover's done. And so at some point in the mission, or several points in the mission, this rover is going to drop these samples back on the ground. And then there will be a future mission that will be coming to bring these, to pick these up. And so we have a choice. We have 38 tubes to fill up with samples. We can do that in a safe place. We can call that a sample depot. And we can go then to more risky places, grab more samples, bring them back to the same place, and put more there. And so that's the whole idea, that we're very adaptable with how we get these samples. And so we're going to be doing this over the course of the mission. We may put a sample cache in Jezero crater, and then we may actually take a bunch of samples and drive out of the crater to another place if this mission is long enough lived, and then possibly even plan to rendezvous with the return craft at another spot. So all bets are off on this. We haven't planned this out yet. We haven't started it yet. So this is kind of where we are here with the Perseverance rover on the left. And then there is another mission that NASA is working on now. They just let the contract for this Mars ascent vehicle. So that'll be the first rocket to come back unmanned from, or uncrewed from the surface of Mars. And so that will only, it's a small rocket. It's only about a little bit taller than a human. And so that is just enough to get these samples into a very low orbit around Mars. And then on the right-hand side, you see this, this canister getting rendezvousing with the larger craft, which will then take it out of the low Mars orbit, has enough energy to get it away from Mars, back into interplanetary space and back to Earth with a return capsule that will bring it down safely onto terra firma on Earth. And so that's the idea. This is going to take a number of years to happen, but we're doing the first part of it here. And that way we can study in terrestrial labs where we have the most delicate and complicated instruments, the things that we couldn't do on the surface of Mars, even though we have some great instruments there. And so with that, I just want to remind you that these instruments are pretty cool. And so here we have Matt Damon. And if you can hear him, if you'll be able to hear him, you'll hear that he is actually taking a lot of comfort from the fact that he found ChemCam, and he's getting a lot of comfort out of having collected it there. So I'm trying to find the button here. Here we go. I'm going to get this going.
Hey, Johansson. I know you don't like it when I touch the ChemCam, but I'm touching the ChemCam a lot.
So I'm going to leave you there. You know, just I want you to stay tuned to whatever happens with these rovers and with the helicopter, which will fly any day now. And I just want to thank you for your attention for this talk. Thanks for being a great audience. And I think I can take questions at this point. I'm going to stop sharing. There we are.
All right, thank you for the talk. We do have some questions, and if other people have questions, please post them into the chat. I'll start off here. a lot of people had questions about the lake in the beginning. And so a few questions here. One from Sarah E. regarding the first image of the lake. How does the water stay in place if the atmosphere is not habitable? And why doesn't the water evaporate? That's a question by Michael.
That is a really big question, actually. And so really up until the landing of Curiosity, the atmospheric climate and climate modelers of Mars were really saying that their models did not show that Mars could support open water over long periods of time on Mars. And now there are other things that they've been tweaking in these models to try to understand, because we have to not only have a relatively thick atmosphere, but also have it warmed enough with a greenhouse effect so that that water will stay as water instead of ice. And so it's a tough challenge because Mars is farther from the sun. And not only that, but we think that early in the solar system history, the sun was actually dimmer than it is now. And so that's something that you could say was defying the modeling up until that point. The modelers have found ways, but it's a little tricky, but using some greenhouse gases to really get the atmosphere thick enough. And there could have been a lot of volcanoes on Mars. It's part of that time that would have kept the atmosphere thick by continually spewing more gas into the atmosphere. Yeah, so that's kind of the confounding thing that we had. Yeah, so.
So we have another question from Gabby V. How would Mars be different if its plate tectonics were active?
Yeah, that's a really good question. And I don't think we completely understand why Mars didn't have plate tectonics, but there's a hint that maybe plate tectonics started in the southern highlands, the most ancient part of Mars' surface, because one of the spacecraft did find some magnetic remnants that suggested magnetic reversals way back then. But Mars would I don't think we understand completely all of the implications. On Earth, we think that the subducting plates actually result in recycling of volatile material, so that it's possible that on Mars, in fact, there was a paper that was published recently that says that because Mars didn't recycle its material, that a lot of Mars water could still be bound up in water-bearing minerals. And so I think we're really still studying the answer to that question. So two good questions there that you could say are still somewhat stumping the scientists.
The next question is from Linda, and it states, are Curiosity and Perseverance really far from each other? So they want to know like the locations of them.
Yeah, so Curiosity and Percy are in the same hemisphere. In fact, maybe the same quadrant, the same quarter of the hemisphere of Mars, but they're about on the very roughly 1,000 kilometers or 800 miles away from each other. I think maybe a little further than that. So they're both sort of on the edge of the northern lowlands. Curiosity is at 4 degrees south latitude, and Perseverance is at 17 degrees north latitude. And I don't have the actual longitudes, but that gives you some idea. But they're a good bit away from each other, but not exactly opposite each other on the planet. And people, I think, always ask, are they going to meet up sometime? And so no, but the next mission would be the first to meet up, because we want to get these samples back. So we want to land right where this mission is next time.
Our next question is from Shivnel. It says, is Mars inhabitable for human migration?
Yeah, so of course, looking to the future, we have this amazing fascination with trying to get humans there to Mars. And it's great because Mars has 24-hour days, day-night cycles. It's 24-hour, 40 minutes. So it's just a few minutes longer than it is on Earth. And in fact, our I and other operations people are living on Mars time right now, which means we're trying to stay in sync with the rover, so we get to go to bed a little later every night. But so that's a great aspect. We have a thin atmosphere on Mars, so both of those things set it apart from the moon in some great ways. The climate, because of these 24-hour days, is a lot more like Earth than the moon actually. But on the other hand, just getting all the resources that we need is tough. And then there's a lot of radiation that is happening on the surface of Mars. And so I think it's been likened to about a CAT scan a week, a CT scan. And if you're in the medical field, you know that no humans should get a lot of those CT scans in a lifetime because they do start to increase our chances of cancer. So for long-term human habitation on Mars, we would have to be shielded, either underground or in some kind of a dwelling that would have enough shielding above it that we didn't have that radiation most of the time. We could go outside, but most of the time we'd want to be in the protection. So that's kind of a reality. So we can go there, send people to explore briefly, but to really colonize Mars, that's got more challenges for sure.
All right, the next question, two of these from Jeff. What other sites on Mars are being studied for the presence of significant amounts of water, polar areas? And also, is there a process for taking hydrogen from methane and oxygen from carbon dioxide to make water for future human habitation?
Yeah, great questions. Let's see, there is a third rover that actually there's two more rovers that we're hoping to get to Mars this year. One is a Chinese rover, and that is called Tianwen-1. It actually has a number of instruments on it. It would be a solar-powered rover, so a bit smaller. And it is supposed to land within about 2 months of now. I don't know exactly when, but sometime in May, June. And so we're really looking forward to that and hoping they are successful. Then there is a European rover that was supposed to launch last year and land now, but it got delayed in part with the COVID pandemic and in part due to other things. And so that is now scheduled to launch in 2022. And I think that one is going to land in Axia Planitia. And so that is going to be a study for the clay minerals, water-bearing minerals that are there. In terms of extracting hydrogen from the surface, from minerals and getting more water, I don't think we really would have to do that. There's a lot of water on Mars in the mid-latitudes on upwards or down or more towards the polewards. There is a lot of water ice that is not far from the surface, so that could be used. And then we don't know how far down the water table is, but there is certainly a water table on Mars. So a deep well could potentially get water almost anywhere on Mars, but it could be a kilometer deep. And then finally, the soil on Mars actually is somewhat water rich, relatively speaking. The Curiosity rover found that, and including ChemCam and the instrument SAM, found that the water is about as abundant in the soil on Mars as it is in a soil in, say, southern New Mexico on a summer day, about 2 to 3 weight%. And that's an amazing amount for a planet that has so little atmosphere. So the water is tenaciously clinging to this soil, and it's very interesting. So we could extract water from the soil for sure. Good questions.
All right, I've got another one from Frantic Flowers. Do you think we will find signs of ancient life on Mars someday, or do you think the radiation has destroyed most of the evidence if there was ever any?
Yeah, well, that's a great question. And just to elaborate a little bit on what the Curiosity rover has found, they found long chain, maybe I said this, long chain molecules, yeah, but no amino acids. So the question is, what would amino acids break down to, and what would things look like? Now, doesn't necessarily mean that life on Mars would have used amino acids, but perhaps something like that, fatty acids. So there are experiments here on Earth. In fact, I was just working on a proposal with a biologist here today to work on irradiating some of our extremophiles to see, maybe in the presence of ice or clay minerals, to see what that would look like. And so we're doing active work to try to understand that whole process a lot more. And then there are ways to get where we are more shielded from radiation. One place is to go where there has been a slight cliff that has been basically moving, weathering away, eroding away over time, and to drill near that cliff, because that would be exposed to the radiation near the surface for a shorter period of time. Things like that. Also, the European rover has a 2-meter deep drill to get about 6.5 or more than 6 feet down. So those are different ways that we're working on getting and then of course to go into Mars Cave is the other way. So all of those ways are ways we're looking to study where microbes, possible ancient microbes could have been protected, as well as understand what would have happened to them over long periods of irradiation.
So here's a few questions from Linda that are all related to each other. So how long is the mission supposed to last? Are there any future rovers planned for launch? And what's a good website if you want to follow the rovers?
Oh, great questions. Yeah, so let's see if I remember them all. So one was about the next rover. I think there was something right before that. Can you remind me what was the first question?
Sorry, so the first question was, how long is the mission supposed to last?
Yes, right. And so NASA started with just expecting a mission to last 90 days back in the Spirit and Opportunity days. And I think I said, one of them lasted all the way till 2018. So we do the testing of the components for these rovers to last for a set amount of time where we think we can get at least part of the mission, a good part of the mission done. And so that those for both Curiosity and Perseverance are 1 Mars year, which is close to 2 Earth years. But we consider that kind of the warranty period. And so if you buy a new washing machine or whatever, you have a warranty on that. And so it's supposed to last at least that long. Now, we can't go to Mars and replace something if it doesn't last through the warranty. But it's supposed to last that long. We've tested it much longer than that. And then beyond that, they kind of say, well, all bets are off, but we think it's going to keep on working. And as you know, Curiosity is working now going on 9 years into it. And we would expect and hope that Percy will last at least that long, and maybe 15 years, but who knows. So is there another rover coming to Mars from NASA? I've mentioned the other international rovers. So NASA is not planning a rover per se. They're planning the sample return, but that involves a small rover, and that rover is called a fetch rover. So this mission will land. It'll have the rocket to get the samples back off, but it has to come and fetch the samples off the ground and put them in the rocket. And so we have this small solar-powered rover that will do that, and that's being designed now. And so that's kind of the plan for now.
Okay, Diana asks more regarding economics. However, what do you think about countries spending millions in the exploration of Mars? Do you think that we can get another economic benefit apart from scientific knowledge?
Yeah, and it's a question that has been asked ever since the moon landing days and before that. And it is, I think it's, there's a lot of different social aspects to that. I think, you go back to a quote by Jesus that says that you'll have the poor people with you always, but we are always working to help feed the poor. And that is our mission as part of our government and as all of the charities that we have in our nation. And so that is of course not just a national goal, but a world goal as well. But there are some real strong benefits to doing these kind of endeavors. And so there are the direct or sort of indirect benefits of the technology that we develop. And then there are the benefits that we get from sort of inspiring people. I was certainly inspired by the Apollo era in the space shuttle. And so that got me to study science. And we have generations of people that are doing that. And they are not necessarily in this line of work, but they're enjoying it vicariously and doing many other things that are moving our economy along, you know, the Bill Gates of the world and so on, of the next generation that will help us with the inventions that we need. And so it is you know, it's always, in my mind, in my opinion, it's a mix between how we use our precious tax dollars in helping the people around us, and then also inspiring us as well for the next generation. So that's my answer.
All right, the next question is from Catherine. I'm curious about the CO2. Is a thought that all the organic material is now in the form of CO2? And also, what determines where and when they gather a sample?
Yeah, so first of all, yes, organic materials with radiation will decay and eventually mostly make CO2. So yeah, that could be a final product. We have, in fact, a conundrum where the Curiosity rover's instrument, SAM, its way of looking for organics was to heat up the sample and drive it off as a volatile organic and then study it. But if there was enough oxygen from things like peroxide or perchlorate that was in the sample as well, the sample would give off a lot of oxygen. It would then react with the organics in the actual instrument and destroy the organics in the very instrument that was trying to sample them. So a little bit of that may have been happening, but there's also other ways that they could get around that. So there's always this interesting sort of unintended consequences sometimes of what we're doing. Yes, so some of the organics would be destroyed on Mars naturally and end up as CO2. Now, the question of where we're going to actually collect these samples and how we're going to do it, that is going to be very interesting. We have a limited number of samples, a limited amount of time, and we want to make the most of this very precious resource that we have. So how do we do it? And so there are a group of scientists that have been selected to join our team that are called return sample scientists. And it's their kind of job, their bailiwick, to figure out and kind of advise us on where are the best places we should go to collect these samples. And there's a variety of samples we want to get. We want to get a soil sample. We want to get different types of rock. And so that's from different places. And then they're probably going to go, like I said, into different depots or caches that we might even leave different places. And so this is going to be a very fascinating thing. And I really encourage you to stay tuned to how this actually gets done. And the other thing, of course, is whether everything works, because it's a very mechanical system. And sometimes, just like the helicopter, we'll run into a little bit of glitches and then try to do workarounds. And so it's always just a very interesting thing to see how everything works and survives on Mars.
Okay, we have a question from Arnold. What's the primary metal used to make the rovers?
Aluminum. And so aluminum is fairly lightweight and fairly strong. Some parts are made of titanium as well, because if you're into aircraft parts, you know that the titanium is much stronger than aluminum. And so those are the two metals that we generally use, but most of it, the rover body, for example, is aluminum. I'll just say one other thing. It's very interesting because aluminum has a fairly high expansion coefficient of thermal expansion. And so between nighttime and daytime, the rover actually increases in height because of this thermal expansion of the aluminum by about 1 millimeter. Not very much, but it's just a very, very tiny bit as it warms up and cools down. So yeah, the choice of metals always makes a difference in the way other things happen.
This question is from Diana. Is it possible that they have gold, other precious minerals in Mars? And I would even throw in, would it be beneficial for us to go mine Mars for any materials?
Yeah, that's great. There are people who have been working on this whole concept of what we call in situ resource utilization. That is to use materials that we find on Mars to create things on Mars, or possibly even ship them back to Earth. That maybe didn't have a lot of steam behind that movement until the 3D printing thing kind of took off. Now the idea is maybe we could 3D print a lot of things on Mars that we would be using there. But that's a little different tangent. You were actually asking about mining and what the precious materials are there. So I can tell you that the ChemCam instrument on Curiosity has found concentrations of copper, which is one of the relatively precious metals on Earth. And so we're trying, of course, Gale Crater was a sedimentary low area, so there's probably a copper deposit somewhere upstream of Gale Crater, and we found it in certain sediments as we were driving along. And so whenever the stream was feeding that part of the lake with sediments, then we would have gotten that copper. So that's very interesting. And we still, with ChemCam and SuperCam, have the intention of keeping on looking around for precious metals. Yeah, it's a very interesting idea. And I hope that someday I can be author on a paper that says, Eureka, we have found gold on Mars.
Okay, Polly has a question. Can the rim facts detect lava tubes, and can they possibly used for use in future missions?
I didn't catch part of that. Can you repeat it?
Yeah, sorry, I stumbled. Can the rim facts detect lava tubes, and can they possibly be used for future missions?
Yes, RimFacts could certainly detect lava tubes if we were driving over one, and if it was within, I think, about 60 meters of the surface. Now, we're not in a lava area right now. We think that there would have been, the jury was out, I think, before we landed, that maybe there was a bit of lava in, ancient lava in Jezero crater. But it's the rocks that we see here now don't look exactly like a consolidated lava flow where we would find a lava tube. But yes, and so we think also we can sort of map where we think lava tubes might be, because sometimes there are collapses that are actually in a row over a series of miles or kilometers. So yeah, there's different ways to try to look for them. Also, there's a radar that is orbiting Mars that I think may be able to see some of the largest ones of these. So yeah, different resources to look for those lava tubes, which could be used for human habitation at some point.
And this question is from Linda. She wants to know how far away the laser can be and still see and hear the results.
Yeah, great question. So the laser on ChemCam and SuperCam works in this pulse mode to zap the rocks. Well, actually, we've used it on iron meteorites. Actually work the best, and so we've found some iron meteorites and shot them up to 11 meters away, I think it is, so that's about over 30 feet away. And but it turns out that sound propagates very poorly in this thin atmosphere on Mars, and very slowly as well. It's only 2/3, a little more than 2/3 as fast as the speed of sound on Earth. And so before landing, we projected that the distance that we would be able to hear those zapping sounds is only to about 4 meters, so about 12.5 feet away. So not very far. We're hearing it pretty well at about 3 meters. So we may be able to go a bit farther. I think maybe that was a conservative projection. And so we need to try it at longer distances. It's been pretty cool because this gives us a source of sound that is a discrete source that's a ways away from the rover. So now we can measure the speed of sound to the rover. And in fact, if there's wind, we can actually look at the different little variations in the speed of sound as it comes back to us. So lots of cool things we're doing with that microphone in ways that we never really thought at the beginning. Good question.
Catherine has a question that I have too, so we'll do it a duo. Is there concern that the samples may contain viral or bacterial samples that may be unique to Mars and not present on Earth? Will that create a contamination?
Great question. And NASA actually has, you might laugh at this, but they have a planetary protection office, and they have a planetary protection officer. And that officer has two jobs within NASA. One is to make sure that anything that is outgoing from Earth to another planet does not contaminate that planet with microbes that could live and spread and then become widespread over that planet. So when we send a rover to Mars, we have to sterilize the parts that are going to be in contact with the surface, and there's rules about that. And then, of course, the other biggie that you're just referring to now is what if we bring something back to Earth? And we have brought back some things to Earth already. Solar wind in a mission that I was in called Genesis, and Stardust in another mission, Comet Dust. But now we want to bring back samples of Mars. Remember that we have meteorites that bring samples to Earth from the asteroids and from Mars as well. But just to make sure that we don't contaminate with a virus from Mars, those samples will be sure to go through some treatments that will be sure to destroy or to render unliving anything that is in those. It's a little bit of a catch-22 because we want to study some of these samples to see if there could have been anything living long ago, but on the other hand, we want to make sure there's nothing living now. So either a heavy radiation dose or all at one time, or else high temperatures, or both, and that's going to happen to all these samples when they come back.
And I believe this is our last question from Cecilia. Please explain why the rover landed near the river delta.
Yeah, so we are most interested in that river delta because on Earth, anyway, organic materials are brought down. Well, first of all, organic materials are water loving. They love water. So you would look for these in a watery environment, in a lake or a river. And then on Earth, the rivers that we have bring down a lot of nutrients or a lot of organic material in the sediments that they bring down. And so we look to a delta formation as being a concentrated place where organics could be concentrated. And in fact, especially in clay minerals, and I showed that the delta is rich in clay minerals. In Gale Crater with the Curiosity rover, we found that the place that was richest in clay was the richest in organic materials. So that kind of fits our hypotheses on that. And that means that the delta should be a great place to look for organics and collect those samples for return to Earth. And that's where we're going to go to get several of our sample tubes for sure. So great question.
All right, well, I want to apologize to the people whose questions that we didn't get to, but I definitely want to thank Roger Wiens for answering so many of the questions. There's been, in addition to questions, a lot of comments in the chat. I know that you can't really see all this flying by, but a lot of appreciation, a lot of thanks, a lot of people saying how interesting the talk has been and the presentation. And yeah, I'm really thankful that you were here and that everything seemed to work in your talk. All the sound, I could definitely hear the little bit of sound and stuff. So thank you so much for your presentation.
Well, thank you, Linda and Daniel, who introduced me, and I just want to encourage everyone to keep on supporting these kinds of missions, and also to support your local community college and your local museum there. they're the people that that host these kinds of events, and they're doing a great job. So thanks again. It's been a pleasure to be with you. And
Okay.
I'll sign off now.
Yeah. Okay. Well, thank you so much. And this talk will be available on the Great Valley Museum YouTube site. So if you want to share it with anybody else that you know, Mr. Wiens, that would be great. And anyone else who's here tonight who knows someone who would have liked to see it, please let them know and come check out the